So when you throw or shoot or project something through the air, it's called a projectile. And the thing about projectiles is that how they move in the x dimension is completely independent from how they move in the y dimension, because in the y dimension, gravity's pulling down on it. But in the x dimension, gravity's not acting that way, right? So we have an object that's accelerating in this dimension, but it's not accelerating and traveling a constant speed, neglecting air resistance, in this dimension. So I've got a projectile launcher here, and this projectile launcher is set up to shoot at a 0-degree angle, meaning this projectile is going to get shot out parallel to the ground. And at the front of it, I have these little connections. I can put a piece of foil in, and that foil completes a connection through this power supply. This power supply runs to an electromagnet, and the electromagnet will hold a target. So what I'm going to do is aim this thing directly at the target, so they're at the same level, right? So here's my projectile, here's my target. They're at the same height. When I shoot this, the ball breaks the foil, releases the electromagnet drops the target, so I'll be able to see something being shot and something being dropped at the same time. So the key here is both of these things have 0 vertical component of velocity. When this ball gets shot out, all the initial velocity is in the horizontal direction. So both of these things are behaving like something that just gets dropped from that height. So theoretically, I should see that both of these things hit the ground at the same time. You can see that even though the shot ball moves forward, both of them are falling at the same rate, so they're always at the same vertical position, and they both hit the ground at the same time. So now let's do something cooler. The object I dropped was actually a camera, so we can look at this setup from the frame of reference of the falling object. And so what we should see is, because both of these things started with no vertical component of velocity, they were both falling at the same rate from the same height, it should look like this thing is just traveling at a constant speed towards the other object, because as they were traveling towards each other, they were falling, right? So let's look at what that looks like. So from this frame of reference, you can see it looks kind of like the ball's just traveling at a constant speed. And in fact, if you focus on just the ball and not the background, it looks just like a ball rolling at you on the ground. Okay, so let's step this up a bit. So I've got my target on the ceiling now, and I've aimed my projectile launcher up at an angle directly at the target. So this is an example of the classic physics teacher demonstration called the monkey and the hunter demonstration, right? Physics teachers, we just love demonstrations. So the premise goes, there's a hunter, and he's stalking a monkey, right? He's aiming at a monkey in the tree. And the monkey is some sort of super intelligent monkey. He can see the hunter, and he knows that the hunter's going to try to shoot him, right? So the monkey's idea is, okay, the hunter's aiming at me. When he shoots the bullet, I'm going to let go of the tree, so I'll follow, and the bullet will keep going, right? So the hunter knows the monkey knows, right? This is one of those things. The hunter knows the monkey knows the hunter knows. The hunter knows that the monkey is like super smart. So the question is, where should he aim to still kill the monkey, right? So should he aim straight at the monkey? Should he aim above the monkey, which is, if you think about it, it's a stupid answer, right? So let's not aim above, right? Obviously that one's dumb. Or should he aim below the monkey, right? So which one do you think? Should he aim at the monkey or should he aim below the monkey? And the answer is, he should aim straight at the monkey. So first off, let's look at this from the wide angle in slow motion. Okay, so let's talk about why this works. So at first, it might seem kind of counterintuitive, right? You think, like if you've ever gone hunting before, you know that if you're shooting something far away, you have to aim above it, right, to account for the drop of the bullet, right? But the key here is that the target is also falling. So when both of these things, again, like the first demonstration, when both of these things let go, the monkey lets go and the bullet comes out of the barrel, as soon as they exit and that one drops, both of those things are being influenced downwards by gravity. They're both accelerating down at the same rate. Right? So first off, let's pretend if there wasn't any gravity. If there was no gravity, right, that's obvious what would happen. The bullet would travel straight at the monkey would let go, but because there's no gravity, he would just float there watching the bullet come and getting ready to kill him. But because there is gravity, gravity's pulling both things down at the same rate. So the monkey falls some distance from its original position, and this bullet is going to fall that same distance from the straight line path that it would have taken if there was no gravity. So let's look at one more view of this, and that's from the frame of reference of the falling target, right? So this is the frame of reference of the monkey who thought he was so intelligent, and he's falling to his death watching the bullet come straight towards him to kill him. So in this case, almost exactly like the last one, if you keep your eye on that bullet as it comes towards the target from this frame of reference, it looks like it's traveling in a straight line at a constant velocity.